Can you see my slides?
Yes, we can see your slides. Yes, there. Perfect. So thank you very much. Now we have our second speaker, Dr. Yongjia Song. He's currently an associate professor in the Department of Industrial Engineering in Clemson University. Dr. Song received his PhD degree in Industrial and System Engineering from University of Madison, Wisconsin in 2013. Dr. Song's research interests include optimization under uncertainty, integer programming, and applications of optimization in transportation and logistics, networks, and energy systems. Dr. Song is a recipient of the NSF Career Award in 2021, and his research has been supported by several federal funding agencies, including NSF, Department of Energy, Office of Naval Research, among others. So thank you so much for accepting our invitation. You can now start presenting.
All right, thank you very much for the introduction and for inviting me to speak here. So today I'm going to talk about a robust bilevel network interdiction problem. And this is joint work with Daniel Silva, who recently graduated from Clemson University, and he's now assistant professor from Florida Polytechnic University, and also my colleague Tom Sharkey here at Clemson. All right, so I'm going to introduce our problem and then talk about our modeling technique, go through some solution methodology, and finally report some preliminary computational results. So our problem is motivated by this application in human trafficking network disruption. This problem can be seen as a two-person sequential game. We have a leader and a follower. The leader is the anti-trafficking agents, and the follower is the trafficker. And the leader is gonna start first by interdicting a subset of arcs up to a certain budget. And then the follower is gonna observe which arcs have been interdicted, and then solve a minimum cost network flow problem to satisfy some market demand using the remaining uninterdicted arcs. So here the goal of the leader is to try to minimize the total exploitation of the victims in the network. And the total exploitation here is measured by the total flow values that is implemented by the trafficker on a set of special arcs. So here's a simple illustration. So we have a trafficker who is controlling a set of victims, and they're forced to participate in different types of illicit markets to satisfy those market demands. And what the trafficker is trying to do is to minimize the total operational cost in order to satisfy those market demand. But the anti-trafficking agents is interested in sort of controlling the total amount of activity for these victims in a specific illicit market. So that's why we have these special arcs that's linking to that one particular illicit market that is the anti-trafficking agency trying to minimize. So we can see that the objectives of the anti-trafficking agents and the trafficker are not necessarily aligned. Something else that is not necessarily aligned is the amount of knowledge. So the anti-trafficking agents may not have the complete information about the trafficker's problem parameters. So that motivates our problem. Our problem is defined as the robust bilevel interdiction problem, or Robin for short. And in our setting, we assume that the leader does not know the follower's operational cost, but they know that it's going to belong to some uncertainty set, which can be learned from perhaps historical data. So here, the leader needs to implement a robust decision to hedge against the uncertainty in the follower's operational cost. And this problem is going to capture both the asymmetry in the two decision makers' objective and also the leader's incomplete knowledge about the follower. So this problem falls into the field of robust bilevel optimization, and this field is still in its infancy, according to Beckett in 2023. So now it's 2026. So right now it is a 3-year-old toddler. Still very few papers are available. So among the few papers that are available in this field, there are two categories. The first category is when the follower themselves is actually facing some uncertainty in their own decision making, and they are going to implement a robust decision. So for example, in back et al. 2023 and 2025, the follower is assumed to solve a gamma robust lower level problem. The second category, which is where our work falls into, is when the leader is actually uncertain about some parameters of the follower problem, but the follower is fully aware of their own parameters. So, for example, in these two papers by Buchem and Hank, they study the robust bilevel continuous knapsack problem. And in our case, we study robust bilevel mean cost network flow interdiction problems. Okay, so now I'm going to talk about our modeling techniques. So we start by introducing some network notation. So we have a network with a set of nodes N and a set of arcs A. And every node has a net supply of Bi, and every arc has a capacity Uij, interdiction cost Rij, which are both assumed to be deterministic. And we have a operational cost parameter Cij, which is subject to uncertainty. So the leader's decision here is encoded by a set of binary variables, gamma ij, which equal to 1 if arc ij is interdicted, and 0 otherwise. And then the follower's decision is going to be encoded by xij variables, and they represent the flow values on each arc ij. The set of feasible solutions for the leader is given by gamma, which is the set of feasible interdiction decisions subject to a budget constraint. And then the set of feasible solution for the follower is subject to this interdicted flow polytope, which has the flow balance constraints and also the capacity constraints on each arc. And if an arc is interdicted, the capacity of that arc drop down to 0. Okay, so now we can present our problem formulation for Robin. It's a min-max mean problem. What the leader is trying to do is to find the interdiction plan that's robust to the uncertain parameters, uncertain cost vector C. And here C is assumed to belong to this calligraphic C set, which is an uncertainty set in this case. And the leader is trying to minimize the total amount of flow going through a special set of arcs, which is represented by beta transpose X. And then X solution must be an optimal solution to the mean cost network of flow problem defined over the interdicted flow polytope that is solved by the follower. So we can see that we are actually focusing on the optimistic version of the bilevel problem. Optimistic version means that in case there is a tie in the optimal solution to the mean cost network flow, the tiebreaker is going to be in favor of the leader. So that's the situation we have here. Of course, if the tiebreaker is against the favor of the leader, then we will have a min-max problem. And that problem will turn out to be much harder to deal with. So we focus on the optimistic version in this talk only. Another assumption we make here is that we assume this calligraphic C uncertainty set is a conic set, which means that if there is a cost vector that belongs to this set, then any positive scaling of that vector will remain in that set. This assumption is actually made without loss of generality because from the leader's perspective, if there is a cost vector that is optimal, then any positive scaling of that will remain optimal because the follower's optimal solution will not change. Because all that matters for the follower is the direction of the optimization of the actual values. Okay, so we can actually accommodate both the polyhedral uncertainty sets, such as a box constraint, and also some discrete uncertainty set. As long as we can take the conic hull of those sets, then we're able to reformulate that in our problem setting. So these two figures will illustrate that point. Okay, so now I'm going to talk about some structural properties, which will help us understand why this problem is challenging to solve. So we are going to focus on the inner problem. So in the inner problem, we already have an interdiction decision that's fixed, and we already have chosen a cost of a vector from the uncertainty set. It is not hard to see that there is a extreme point solution from this interdicted flow polytope that is optimal to the inner problem because the set of optimal solutions to the mean cost natural flow problem is itself a polyhedron, and we are minimizing a linear function over that. So there must exist an extreme point that is optimal. Another thing that we can observe here is that the interdiction decision cannot introduce new extreme points. So the set of extreme points of the interdicted flow polytope must be a subset of the original set of extreme points of the flow polytope. So by combining these two lemmas together, we only need to focus on the set of extreme points of the flow polytope and understand how the interdictions can impact their optimality. So let's see how we can characterize the optimality associated with the extreme points. So in fact, that can be characterized by the so-called C-cone. So C-cone is defined as the set of cost vectors such that under that cost vector, this extreme point is preferred than every other extreme point. And we also take the intersection with the uncertainty set so that at least it is feasible. So below is a figure that illustrates this point. So assuming that the uncertainty set is a whole space, then every single extreme point here has associated C-cone. So now if we apply some kind of interdiction, so for example, we interdict extreme point x5, then we can see that the C-cone of x1 and x4 actually gets enlarged, and the C-cone of x2 and 3 will remain the same. And the reason why interdiction can actually enlarge the C-cone of the remaining extreme point is that some of the extremes are removed, so that the set of some of the constraints that used to define the C-cone will get removed, so the C-cone will actually get larger. So that's a very important sort of a structure of our problem. So now we can understand this kind of challenge of solving this problem from an intuitive perspective. So we can see that the interdiction is actually a double-edged sword. So on one hand, the interdiction can obviously help you by removing those unfavorable extreme points by directly interdicting that. So you can just avoid having those extreme points. You can also make the favorable extreme points to be optimal to the Fowler's problem because the corresponding interdicted C-cone will get larger and essentially become non-empty, so that those favorable extreme points will potentially become a candidate solution to the problem. But on the other hand, it also runs the risk of making other unfavorable extreme points to be optimal to the Fowler's problem, so that you will have to hedge against with those. So essentially, your interdiction will have this kind of trade-off between these two effects. So that's why this problem is challenging to solve. Okay, so now I'm going to talk about a solution methodology to solve the problem. This is the exact solution approach. We're going to apply the celebrated C&CG framework, column-and-constraint generation framework. So to be ready for that, we first of all need to reformulate the problem so that we have a single level inner problem. That is not hard to do because we have a mean cost network flow problem in the constraints. So we can actually use the strong duality of LP to reformulate that as a single level problem. We're going to take the dual of the inner LP of this mean cost network flow problem and arrive at this C&CG friendly reformulation. We have a mean max mean, and the inner problem is a linear program. So this linear program contains the primal feasibility constraints. That's the interdicted flow polytope. We have the dual feasibility constraints, and we also have the strong duality that ensures the optimality of the X decision. All right, so now we can apply the C&CG framework by breaking down the problem into a master problem and a subproblem. In the master problem, we are going to use a partial representation of the uncertainty set. We're going to have a finite number of cost vectors that we enumerate, and that's only a partial representation. So by solving the master problem, we only get a lower bound to the original problem. And at the same time, we get an interdiction solution that we can evaluate its objective. And the idea here about the master problem is that for every cost vector C bar that is in this partial representation, we're going to associate that with an optimal solution from the set of optimal solutions to the mean cost network flow problem. And we can use the strong duality of the inner LP to enforce that. And also the first two constraints here will ensure that we select the interdiction decision that is robust to all of the C vectors that we have encountered. So once we have solved the master problem, we have a new interdiction decision. We can solve the subproblem, which is given below, to get a new vector C, which will be included in the master problem in the next iteration. And we also get to evaluate its objective. So we have an upper bound associated with that feasible interdiction. So we can update that in the next iteration. So the subproblem here is itself a max-min problem, but luckily, again, if we fix C decision, then the inner problem is a LP. We can take the dual and combine that with the maximization, and this is the standard dualize and combine approach to reformulate that as a single level maximization problem. Okay, so now we have the master problem and the subproblem in place. We can describe the algorithm. So we start with the initial interdiction decision. We are going to set some initial upper and lower bound. The initial partial representation of the uncertainty set can start with empty set, and then we go into the loop here. We're going to solve the subproblem to get a new C vector and get an upper bound. We're going to update my partial representation by this new C vector and update the upper bound, and then add the variables and corresponding constraints to the master. So now we have a bigger master problem with additional variables and constraints. I'm going to solve that master problem to get a new interdiction decision and update our lower bound. And this procedure goes on and on until we have a convergence between upper and lower bound. So this procedure will have a finite convergence guarantee, because if the subproblem does not provide a new cost vector that induces a new extreme point, then we can see that the upper bound will coincide with the lower bound. So then the C&CG algorithm will for sure terminate. And we only have a finite number of extreme points to start with, because all the possible extreme points are from the original flow polytope. So that guarantees the finite convergence of this C&CG framework. Okay, so before we talk about some numerical results, I want to emphasize the challenge of solving the subproblem. As we can see that the reformulated subproblem is very challenging because of the bilinear terms that's showing up in both the constraints Cij times C and also the objective Cij times Pij here. To make things worse, these variables Pij and Z that's involved in these bilinear terms actually do not have a good bound other than the sign restriction. So this is going to make the solvers very struggling to solve this to optimality. So we have a very important observation here, thanks to the conic uncertainty set assumption, which is, let's say we have obtained the optimal solution to the subproblem with C hat, Y hat, W hat, P hat, and Z hat, and Z hat value is positive. Then we can actually find the alternative optimal solution by scaling the Z values to be 1, and then scaling P values and C values accordingly. Then we can show that this is actually an alternative optimal solution, and it is totally legal to do that because we can scale the C vector by any positive amount and to stay in the conic uncertainty set. So this means that we only need to focus on two cases for solving this subproblem. One is when Z equal to 0, which we are unable to do this scaling. And if we're able to do the scaling, we can only focus on the case when Z equal to 1. So we only need to solve two cases for this subproblem. And that's what we're going to do. So if Z is equal to 1, we can see that all of these bilinear terms will disappear from the constraints. And because of that, by looking at this constraint in the box and also the sign restriction on Pij, we can actually fix Pij equal to 0, and that will be used to remove that bilinear term in the objective. So when Z equal to 0 is actually very simple to solve. We can actually see it's actually the dual of the mean cost network flow problem. When Z is equal to 1, we will get rid of all of the bilinear terms in the constraints, but we are going to still have a bilinear term in the objective. But the good news is that now we have a explicit lower bound on Pij thanks to these constraints. So this will give a big relief to the solver to help solve this problem much more efficient. But still, the subproblem remains to be the most challenging part in our computational performance. Okay, so now I'm ready to talk about some preliminary results. So we have a uncertainty set that is imposed on all of the arcs that's connecting to the market demand node. And we consider a discrete box constraint with the discrete intervals randomly generated with 11 values between these two ranges. And we created three networks of different sizes using the network generator for human trafficking networks, small, medium, and large. And as the size of the network increased, the dimension of the uncertainty set actually also increased dramatically here. Okay, so first of all, we're going to compare the performance of solving the subproblems using our conic structure exploiting approach versus the solving that directly by Gurobi. We just randomly generate five interdiction plans for each interdiction budget level, 2, 4, and 6. And we can see that our conic approach is able to solve all of those instances within half an hour. But the Gurobi cannot solve them most of the time within the time limit of 2 hours. And even if they can solve it, but in many cases, they run into numerical issues so that we cannot get anything useful out of that subproblem. So basically, the conic structure exploiting approach will significantly outperform this direct approach. Okay, so now we are going to look at the performance of the C&CG algorithm. So we apply a 1 hour time limit for solving the subproblem and 8 hours for the overall C&CG. And whenever the subproblem time limit 1 hour is met, we're actually going to check if it generates a different C vector. If it does not generate a different C vector than the ones that already exist in the master, we are going to use the remaining time to solve that subproblem because that turns out to be the bottleneck of the whole procedure. And also, we're going to initiate our interdiction decision by solving a deterministic mean cost network flow interdiction problem, where every arc will have the minimum cost realization if it is an uncertain arc. Okay, so we have those results for small, medium, and large. We can see that for small and medium instances, the C&CG framework can solve them very quickly. But it struggles a little bit for solving the larger network instance. A few quick observations. We can see that the algorithm struggles the most for small interdiction budget, and that is perhaps not surprising because if the interdiction budget is small, the remaining network is large, and that is where the subproblem is solved on, and subproblem is the bottleneck in our computation. Another interesting thing we see here is that we have a relatively small number of iterations for the C&CG to converge. And this is due to the alignment between the leader's objective and the follower's objective. And we do not have to explore many extreme points to allow this algorithm to converge. Okay, so to wrap up, we have studied this Robin problem that's motivated by human trafficking disruption under incomplete information. We have proposed a C&CG method with a conic structure exploiting approach to solve the subproblem to achieve some considerable acceleration. And in the future, we would like to pursue the pessimistic version of this problem, which is much more challenging to solve. And we also look at the extension to cases where the leader is interested in some discrete measures as the objective. So instead of minimizing the total amount of flow on the set of special arcs, we're interested in minimizing the number of arcs in that special arcs that carry a positive amount of flow. This has been studied in one of our prior work, and we believe that the C&CG framework can be extended to handle this case as well. So finally, I would like to acknowledge the support from the National Science Foundation for this research. Thank you.
Thank you so much. So we have a few minutes if somebody wants to, if somebody have any question. Otherwise, we will start the break rooms. Okay, it seems like everybody's a little bit shy today, so we'll create two break rooms, one for each speaker, so you can just join in and ask them directly if you have any question about your talk. So thank you again, Jornia and Emma, for being
Yes,
here.
and don't forget to join us next month
Exactly, yeah.
for especially those of you watching online, because we'll stop the recording in a second.